Oh, hi. Before we got the tape going, I put this turpentine can on a hot plate and put maybe about an inch of water inside there. And I heated it up so that it started boiling a little bit. I noticed a little bit of steam. I'm going to put a rubber stopper in here and let it cool. During this little exercise, we'll keep that up front and see what happens. So inside here, a little bit of boiling water, lots of gas, just air, and then it's now a closed system. It's going to start to cool down. I made this model, just very simple, an H2 molecule, and the exercise is how fast would this be going inside this room right now? We have some conditions. We are at 1 atmosphere, plus or minus a little bit. I'll just call it 1 atmosphere. We're at about 298 Kelvin room temperature. The mass of this, it's 2 grams per mole. I'm not going to use 1.0079 grams per mole times 2. I'm just going to say this is 1 gram per mole, this is 1 gram per mole. So we have 2 grams per mole. We have a little equation to talk about how fast this thing's going inside this room. And the equation goes like this. Mu RMS. Mu is used in gas treatments to be the average velocity, but it's a particular type of average. We call it the root mean square. We'll say that some gas molecules are traveling faster, some slower. We'll say most of them are traveling very, very close to this calculation. They are zipping by our face and hitting us and bouncing off the walls very, very fast. It's equal to the square root of the number 3 times R times the temperature. So on the top, I've written 3RT, quite straightforward, over the molar mass. This calculation is greatly simplified if we use not R, 0.0821 liter atmospheres per mole Kelvin, but if we do some unit conversion on that R. It's still a constant, but we've changed the units. It's like saying this length is 1 yard, this length is 3 feet. It's the same, we've just switched the units and done the conversion. We're going to use another R value with new units. Same R, mu RMS is equal to the square root of the number 3 times 3.14 joules over moles times kelvins. A mole will cancel with the molar mass in a moment. Our kelvins will cancel with the temperature. A joule is a unit of energy, and it's essentially a, kilogram meter squared over second squared. So things will work out canceling just nicely in a moment. The temperature was measured in the room to be 298 K, very typical room temperature. On the bottom, we have 2 grams per mole, but bear with me for just a moment. Let me tell you, when doing this, the joule does not contain the unit of gram for mass, it's kilograms. So I would like to change this into kilograms. I'm simply going to slap a times 10 to the negative third on there, because a kilogram is 1/1000th of a gram, and we're going to end up with, instead of grams per mole, 2 grams per mole, divided by 1,000, which I've done here, and we get kilograms per mole. The moles will cancel. Let's see, the kelvins will cancel. A joule is a kilogram meters squared over seconds squared, a unit of energy you might remember from a high school science class. The kilograms will cancel, leaving us with the units of meters squared over seconds squared. Everything's going to be okay, because we're going to take the square root of the number and the units, and it'll leave us with meters per second, which is good for a speed or a velocity. I'll do that in a second. You may have noticed this has been crinkling up a little bit. It's been making some sounds. It's been going. And the reason is gases above here are cooling. So think about what the effect is on this can. Would the can be expanding or contracting as the gases cool? Let me do the math. On my calculator, I'm going to plug these in and come up with an answer. Mu RMS is equal to some number. And again, units will be meters per second. Go ahead and you do that, and I'll check back with you in a minute. So we've got 3. I'm hoping you have nearly 2,000 meters per second. I'm going to write down 1928 meters per second. Let's go back and kind of examine. I used 2 grams per mole, giving myself only 1 sig fig. Let me just call this 2 point, no, I can't even call it 2. point, I'll just call it 2 point without any zeros, times 10 to the third meters per second, or 2,000 meters per second. So these molecules inside the room, made out of hydrogen, right here at room temperature, 2,000 meters per second.